Hello, today I'll be talking about automatic repeated request protocols in networking. So more specifically, this is for the transport layer. So in the transport layer for the IP model, we had previously some different protocols that we could follow, such as UDP. And UDP doesn't provide any guarantees when it comes to the reliability of transferring packets over the network. So as part of that, you can implement some of these protocols that essentially provide all the security and retransmission of packets as it gets sent over a network by following these basic steps. So essentially what we're going to do is we're going to build a reliable data transfer protocol, RDT for short. So this will be a reliable protocol. So let's begin with the very basic version, and the very first version that I will call will be called RDT 1.0. Now RDT 1.0, effectively what this will be is this will specify the very first version of it. So we're going to be using finite state machines for this to essentially indicate how state will move from one event to the other based on events. So effectively we're going to have states which are marked by circles and then arrows as we navigate from state to state based on some event or trigger. So the way this works is in RDT 1.0, this is going to be the very first one. We're actually going to assume that there's no bit errors. So assume no bit errors. And similarly, we can assume that there's no loss of packets. Okay? So we're going to have two different components. We're going to have the sender and then the receiver. So the sender will be sending packets over to the receiver over this currently reliable network. So the very first thing in a finite state machine is we have the sender over here, which is this circle over here, which waits for a call. And then so sender waits for an invocation. After it receives an invocation, what it's going to do is it's going to do reliable data transfer send, aka it'll create the packet and then send it. On the other hand, for our receiver over here, we're going to have something like wait to receive packet. Start state. So anytime we do an RDT receive, we're going to extract the data from into our data, and then we're going to deliver the data to the application. So we have these two sides to the equation. We have the receiver over here, and we have the sender. So the application sends data to the sender, and then the sender transmits it over the network, assuming no packet loss, over here to the receiver's end. Now, we did two bold assumptions. We said assume there's no bit errors and assume there's no loss of packets. But now we have the problem. We have the problem that when you're sending data over the network, some of the bits could get lost. So depending on the type of cable that you're using for the guided or unguided media, so guided media meaning that there's actual cables, so you could use a coaxial cable, you could use just copper cable, or you could use a thing called HFC, which is hybrid fiber coaxial cable. Depending on the type of cable, some of the bits could get flipped as part of it. So that could be because of magnetic intrusion, so another electromagnetic field which is flipping some of the bits, or the actual wire is being bent, which causes the light to bounce inside the wire. So of course, because of those reasons, it's possible that some of the bits get flipped. So one way is to actually guarantee, hey, have my bits been flipped? So there is actually no way in networking to have a 100% guarantee that you can verify this unless you have a specific thing that you're expecting on the other side, like a specific bits that you already pre-know. So as long as you're sending bits over the network and you're not sure of what to expect on the other end, there is no way to 100% guarantee that you're going to get the same packet. But we can probabilistically say, using generating a hash value based on the bits, we can generate and verify the C using something called a checksum. So what we're going to do is we're going to use a checksum to check for bit errors. So this will be in our RDT 2.0. So we're going to use a checksum, and the way UDP implements checksum is it actually uses 16 bits. And the way it uses 16 bits is that it goes through all of the different, every 2 pairs of bytes, and adds the ones complement to each other. So after adding the ones complement for every single pair of 2 bytes, then we go through the entire packet and we generate a checksum, which is a hash value of all the bits. Now, of course, there is a probabilistic chance if some of the bits get shuffled, that resolves to the same hash value because there's hashing collisions. So that's what I meant by it's probabilistic, but it's no guarantee that this is actually the case. So how do we actually do this? So we're going to keep our previous states, but then we're also going to store this checksum value, and then if the checksum value fails, what actually happens to the finite state machines? So what actually happens to the finite state machines is that we're going to have some sort of way to acknowledge the request, which is what we're going to be using as an ACK or NACK. It essentially says, yes, I acknowledge the request, or NACK, no, I don't acknowledge the request. So this is part of the RDT 2.0. This will be channels with bit errors. So we're going to introduce 2 new things inside of our mechanism, 2 new mechanisms. We're going to have acknowledgements, ACKs, and NACKs, along with our checksum capability, which is inspired by UDP's checksum capability. So UDP provides checksums, so does TCP. So we have that in our favor. So now it's slightly more complicated. We have a thing here. So we're going to wait for an invocation for the very first step. And then after we send the data, we are going to wait for an ACK or NACK. Okay. So this is part of the RDT send. And then inside here, what we're going to do is we're going to repeat this step for every single NACK that we get. So if we do RDT receive packet, and it's an NACK, then we do UDT send packet again. Otherwise, if it's an ACK, then we can just finish. So if we do RDT receive packet, then we're done. We can go back to the invocation state. On the other hand, for our receiver, what we're going to do is we're going to have this not corrupt method. So we have that checksum value passed in as part of the packet. We're actually going to analyze the packet and then compare it with the checksum value. So there's 2 cases here. Either bits can get flipped within the actual packet, in which case it'll cause your checksum to be wrong, or maybe the bits flipped inside the checksum, or both. And probabilistically, in either case, it's possible that the hashing resolution resolves to the same hash value because of the collisions. So in either case, there's no guarantee, but probabilistically, it's very unlikely that that happens. And as such, we say that it's good enough, essentially, for the purposes of reliable data transfer. So again, we have another one like this. It says, wait to receive data. And here we have 2 cases. We have case 1 where we receive data and it's not corrupt. Receive packet. In which case we're gonna extract it, extract the data, and then deliver the data to our application. But more importantly, we send an ACK back, and in the other case, we still loop back here, but it's corrupt. We send a NACK. Okay? So this is generally how it works for both our sender and receiver. Okay? This is RDT 2.1. So essentially now we handle the case where there's bit errors, but then we have the case where, hey, what if the actual packets get lost? There's a lot more that we have to do. Also, what happens if an ACK or NACK gets corrupted? Then the sender won't know what it actually received. So we can't just retransmit because maybe we'll get a possible duplicate. So instead what we should do is we should add sequence numbers to every single packet. So that way, the receiver will discard any duplicate packet that it receives. So the way to do this is we're actually going to add a sequence number to each, and then we can alternate between zeros and ones. So that'll be the fundamental basis of and motivator of RDT 2.1, which is our next generation reliable data transfer. So the idea of this is that if we have sequence numbers zeros and ones, and then my sender sends a packet with sequence number 0 twice, then we automatically know to discard it because we're waiting for sequence number 1. So here we're assuming there's no delayed packets, but we're also handling the case where our ACKs will get corrupted. So we won't actually know, do we need to retransmit the data? Because if we get an ACK, then we don't know, or we get some unknown value, we don't know. So then we could get duplicate packets. So that's the motivating factor between the other RDT. So I won't actually go over the finite state machine for this, but I'll describe it in depth because it gets very complicated. But effectively what you need to understand is there's two components. Just like before, we have our sender and our receiver. Now, there's two states that we're handling here. And these two states are zero and 1. So that when we send back a packet, it can either be an ACK, NACK, or the actual ACK or NACK packet got corrupted. So if the actual ACK or NACK packet got corrupted, before we had a state here that says, okay, we're currently on sequence number 0 or 1. If we're currently on sequence number 0, and we send back a sequence with 0, right? And here where we said, okay, with sequence 0, we sent an ACK, which happened to get corrupted, and then we're expecting sequence 1, but we received back a sequence 0. We automatically know that we can just discard that packet, because we've already acknowledged that. We said we already expected it to go through. We can just send an ACK back. We don't need to register that. If we didn't have this mechanism, when we send the corrupt packet back, we don't actually move forward in sending the next type of packet, so we end up with duplicate results. On the other hand, if we sent a NACK, then on the receiver side, we would have remained at 0. So then the sender over here would resend that 0 packet again, because it received a corrupt packet, which we don't know which case it is. So it sends it again, and then this one will try to send a NACK back later, hopefully, as long as it receives it now corrupted. So this will handle the case where we have ACKs and NACKs that can also get some bits scrambled around. So now that we have this, then we have a little bit more of a problem. The next suggestion we have is maybe we can actually eliminate the NACKs altogether. We might not need NACKs. So the way to do this is is that we're actually going to only use ACKs for this, and instead of a NACK, receiver sends ACK for the last packet received OK. So this means that the receiver must explicitly include the sequence number of packet being ACKed. So this way, if we get a duplicate ACK at sender results, it results in the same action as an ACK, so we retransmit the current packet. So that's just a small little modification on RDT 2.1, where here we just simply have an ACK-free protocol. So RDT 2.2, no NACKs required. But this is very minor and it doesn't actually add much. It just reduces the states that we have to deal with. Now RDT 3.0 is a more interesting one. So RDT 3.0 resolves our other issue. What if we have packet loss? So before we covered the case where we had bits missing. So if we have bits missing, then okay. We figured that out using the checksum, we generated the hash, we saw that there's a collision. But now what do we do if there's actually a packet missing? In our previous one, we just kept waiting and waiting and waiting. Our finite state machine never progressed in a periodic manner unless we actually received some input. So the other one would actually freeze. It would just keep waiting and then it would never receive. The sender wouldn't receive anything because it's waiting for an ACK or a NACK. And then the receiver would just be waiting there forever. So instead what we're going to do is that for the sender, we're going to be waiting for a reasonable amount of time for an ACK. If it doesn't receive anything back from the receivers, and in terms of an ACK or NACK, we can safely assume that the packet got lost in transmission and that we need to retransmit it. So this also accounts for the case of the sender losing its packet. We will just simply send it again. Recall that we're using the sequence numbers 0 and 1, which are alternating, and it's sufficient for our case. So in this case, we can actually just simply deal with retransmitting it from the sender, and this will automatically handle any duplicates in case the packet got lost while it's being sent from the receiver's end to the sender's end. So the way this is implemented is actually using a timer approach. So we're going to pick a timer, and then based on that timer, we can actually decide when we want to retransmit the packet. If we retransmit the packet, then we will safely be able to do it again. And this is the foundation for it. So I'm going to go through some examples how this is implemented. The advantage of this is that, again, now we handle both cases that we originally mentioned. So I'm not going to do the finite state machine for this either, but what I'm going to do is I'm going to instead show RDT 3.0 in action. So here's how it looks like. So we're going to have a sender here, and we're going to have a receiver here. So the very first thing is we're going to send packet 0, sends it off to the receiver, then the receiver receives packet 0, then the receiver sends packet 0, ACK 0 back, then this guy receives packet 0, ACK 0, then we send packet 1, receive packet 1, we acknowledge packet 1, receive packet 1, send packet 1, and so on and so forth, okay? But now let's consider the case where what actually happened was that we had a delay. And then while we were sending ACK 0, something happened on the network. And we got some packet loss, okay? Something happened here. So some time frame t will pass by, and then inside here, timer will expire. Okay? When the timer expires, we're actually going to resend the previous packet. So we received packet 0. The receiver was actually expecting packet 1. So we received a duplicate, but because we have this alternating system of sequence numbers, we automatically know that we just need to resend it. We don't actually need to acknowledge it. So we resend it. So we do acknowledge packet 0, and here we receive ACK, and we send packet 1 back. Receive packet 1, and we acknowledge packet 1, and we keep doing this back and forth. Okay, so this is the fundamental idea. But now I'll be covering some performance characteristics. What are the actual performance characteristics of these reliable data transfer protocols that we just developed? So what we do is that the performance we realize sort of sucks. So the actual transmission time of it is expressed as L over R, where L is the load and R is the actual utilization, so total speed that we're going at. So what we do is we notice that if we're sending, for example, over an 8,000 bit packet, for the transmission, we're going to be having something over at the speed of light. This is to send an 8 kilobit packet. Okay? But now we're interested in saying, okay, what is the percentage utilization of our sender? So our sender, how much are we actually utilizing the sender? Because we're waiting to receive the packets back, so we're sending this over the network. So the U sender is equal to L over R divided by round trip time plus L over R which equals with 0.008 over 30 plus 0.008. Equals 0.008 over 30.008, which is 0.00027, which sort of sucks. So this is assuming round trip time is 30 seconds. So effectively what we have now is we actually have a diagram that looks a little bit like this. So we're going to have on one end, we're going to have our timeline over here, like that. And then we're going to be sending our packet like this. Over to our receiver's end, like so. Now over here, we're going to have time equals 0 over here. And time equals L over R, whoops, over here. And then we have our round trip time, which will be this segment over here. And then we get our return that looks like this, which is the ACK that we're receiving back. So the total time that it took to transfer everything, so the time is going to be equal to L over R plus round trip time. So we have our previous formula for the utilization of the sender. What we notice here is that we're actually a little bit inefficient in sending this data. So this over here is the transmission time. And then this over here is our round trip time. But how about instead we do something called pipelining, where if we have another one over here, instead what we do is we send one packet here, but instead we send another packet right after it, and another one. So we still have our original t equals 0 here, but we have a round trip time from here all the way until here. But in that time frame, we actually sent 2 more packets, right? So our network utilization is actually significantly better because in the same time frame, our network successfully utilized 3 more packets. So we have a linear increase in terms of the amount of things that we're pipelining in this process. So if we successfully do this using pipelining versus sequential from here, we will successfully be able to change this equation and get a different result. So the stop and wait is significantly slower, but instead if we do this technique, we're going to get an equation that looks similar to this. We're going to get that U sender. So U sender. So the utilization of sender is 3L over R divided by round trip time plus L over R, which equals with 0.0024 over 30.008, which is 0.00081, which is in fact, it increased the 3-packet pipelining, increases utilization by a factor of 3. Okay? This is very nice. So we increase utilization by a factor of 3. And what this is very nice is that we're actually able to fit more packets all into one. But how does this actually work? How do we do pipelining if one of our issues is that our sequence numbers are 0s and 1s? We can't possibly send 3 packets all at once because we have sequence 0, we have sequence 1, we have sequence 0. The receiver doesn't know which packet you're actually receiving. So instead we're going to be going through something called AQR. And AQR is something that's called, ARQ protocols. And ARQ protocols are defined as automatic repeat request protocols. And more concretely, we're going to be discussing 2 types of protocols here. One of them is called go back N, and the other one is called selective repeat. So I'll be talking about this more in my next video, so just to break up my videos into half, and then we're going to see how these two protocols are implemented, pros and cons of each, and then we're going to go through some sample cases on how they're implemented as well. So yeah, thanks for watching, and stay tuned for the next video. I'll put the link in the description so you can just click on it, and thanks for watching.